Welcome again. SQAB Tutorials 2003. It's a pleasure to introduce John Wixted, professor at the University of California, San Diego. And he has been, well, a remarkable contributor to our field. He has worked in reinforcement schedules. He has contributed to work in behavior therapy. And the majority of his recent career has been in work in areas that would ordinarily be called memory and cognition, and are in fact called memory and cognition. And he has published in a wide variety of different journals, including Learning and Cognition, Memory and Cognition. He served as the editor of Psychological Bulletin and Review. He's been associate editor of Memory and Cognition, and as well as Journal of Experimental Analysis of Behavior. So in effect, he is like a living link between the fields of cognitive analysis and behavioral analysis. His work on memory has had quite a substantial effect in the field. And a good deal of it has been informed by signal detection theory, or perhaps more generally, thinking along lines suggested by signal detection theory. It provides us not only with a sort of a calculation machine for working out parameters, but also with a way of approaching problems. And I think that's the most general lesson to be derived from it, which I suspect he will give us. John has received a number of distinguished teaching awards, so I expect his presentation will be especially clear. John, take it away.
Okay, thank you, Tony. Okay, well, my talk today is on what is sometimes referred to as classical signal detection theory, and I'll be focusing in on something called ROC Analysis. ROC stands for Receiver Operating Characteristic, but usually just referred to by ROC. And this theory is one of psychology's most important contributions to the world. In fact, I would say it rivals behavior analysis in terms of what it has to offer the world. And between behavior analysis and detection theory, that's pretty much all psychology has to offer the world, I think. As just sort of indirect evidence that detection theory is regarded by many as an important contribution, there's a journal, a new journal called Psychological Science in the Public Interest. And it's put out by APS. It started in the year 2000, and it addresses areas in which psychological science can inform and improve public policy. That's the purpose of this journal. It's all about what psychology has to say to the world at large. And Volume 1, Number 1, the inaugural issue, had a paper in it called Psychological Science Can Improve Diagnostic Decisions by Swets, Dawes, and Monahan. And it's all about signal detection theory and ROC analysis. So that's just sort of indirect evidence that this is something worth knowing. And I bet you a lot of you out there are thinking to yourselves, yeah, I know the signal detection theory is something I should know, but I really don't. It's on my list of things that I should learn, but I haven't learned it yet. So hopefully I can add something to it. So it's all about decisions. Signal detection theory applies to decisions like these, and the kind of decision is something present or isn't it? And that kind of question comes up in just almost every area. And here are some areas where it comes up. A radiologist is looking at an MRI or an X-ray or something and has to decide, is a tumor present or not, according to what I'm looking at. A diagnostician, some of you maybe have had to address a question like this: does this child have autism or not? An airport screener has to decide, does this suitcase contain a bomb or not? A patient who is maybe testing out a new analgesic or something, did that stimulus cause pain or not? And experimental subjects in a human memory experiment are asked the question, did that item appear on a list or not? So these are whenever the question is framed like that, the concepts of signal detection theory apply. And when you do apply those concepts, it usually sort of elevates the discussion a bit. It suggests some things that you wouldn't have thought of otherwise and that are worth knowing about. So I'll start, first I'm going to point out that the basic data that you focus on are hits and false alarms. And to illustrate what those are, I'll talk about a bomb detection device, some theoretical bomb detection device in an airport that scans bags as they go through. Let's say somebody has one of those. We have them now. And a critically important consideration that I have to mention right off the bat, which might seem obvious but is often forgotten, is that in lots of situations where the question is something present or not, you have to realize that there are two states of the world. Some bags have a bomb, some don't. Those are the two states of the world that you have to worry about. And usually very often people forget about one of those states, like some don't. So when people, early on when they were trying to sell the government these bomb detection devices, they'd focus only on what is called the hit rate. That is, you might test this device by taking 100 bags with bombs in them, putting them on the conveyor belt, and see how likely it is that bomb detection device sounds the alarm and says, I think there's a bomb in that bag. And you might find, if you test it that way, you send 100 bags down the conveyor belt, that it sounded the alarm in 84% of the cases in which a bomb was really present. And so that's an 84% hit rate. It got 84 out of 100. And often, when these devices were advertised, they would focus only on that hit rate. And that sounds pretty good. And other devices would have a 100% hit rate, and it sounds like a pretty good device. But if you were, a behavioral consultant brought in to investigate the operating characteristics of this device, you'd also want to know something else. You'd say, well, don't forget that some don't have a bomb. And you can't just assume that it's not going to react to those bags. You actually have to test it and see how it reacts to those bags too. And when you do, you might find that it responds positively. Send 100 bags down the conveyor belt without a bomb, and you might find that it responds positively in 16% of those cases. That's the false alarm rate, the probability of sounding the alarm when there's nothing really there. And that's the first step. That's a slightly non-intuitive. Usually people want to focus on percent correct. So the natural thing to focus on would be percent correct in this case, which that's the hit rate, and that is a percent correct measure. 84% of the time it got it right. And your natural inclination would be to focus on a percent correct measure in the other state for the bags that don't contain a bomb. But in signal detection theory, you always focus on the complement of that, the false alarm rate. So instead of saying they're 84% correct, you focus instead on the fact that it's 16% incorrect. And so what you're focusing on is not proportion correct, but probability of detecting a signal or sounding the alarm that a bomb is in a suitcase. So this sounds the alarm in 84% of cases when a bomb is present, and sounds the alarm in 16% of the cases when the bomb is not present. And 16% false alarm rate might seem like something of a problem after all, because that you have to stop and search the suitcase and things like that. So a false alarm is a bad thing. And actually, I'm not going to be really talking about base rates today, but in this one practical situation, that 16% false alarm rate is a really big problem because the base rates are unequal. That is, there's something like, maybe it's even worse than this, 10 million safe bags per bag with a bomb. So the vast majority of bags don't have a bomb in them. So you're going to get like 2 million false alarms per detection. And that might just make the thing impractical. If too many times you're going to stop the conveyor belt, search the bags, and so this device may not be that useful. And so what you might want to do is see if you can adjust that false alarm rate downward. And you might adjust the sensitivity knob on this machine to make it to a more conservative setting, to make it its own internal signal has to be stronger before it sounds the alarm. Okay, so you adjust this knob so it's not going off so often. And when you do that, well, one price you pay is that the hit rate goes down. So instead of catching 84% of the bags with a bomb, it's only going to catch 50% of them. But the good thing is the false alarm rate goes way down to something like 2%. So you'll only have maybe 400,000 false alarms per accurate detection of a bomb. And so when that sensitivity knob was adjusted, the thing to focus on here is that both the hit rate and the false alarm rate went down. And that's really all ROC analysis is. It's investigating the relationship between hits and false alarms as you adjust something analogous to a sensitivity knob, and people have such knobs too. Okay, so let me give you a completely different example, and I'm going to give you several examples today so you get the idea that this is a generally applicable way of thinking, and that it helps you think about things that you might not otherwise think about. So in this case, it helped people think about cases other than the hit rate. You had to focus in on the false alarm rate, which is a big problem. Oh yeah, first I want to tell you basically how signal detection theory conceptualizes a hit and false alarm rate. And actually, this is in any signal detection analysis, this is the most important step, to draw the picture. And so let's walk through this picture so you see how it works. So some of the bags, let's say 100 bags down the conveyor belt actually have a bomb, and those are the targets. And another 100 bags don't have a bomb, and those are the lures. And those 100 bags with a bomb in it generate some signal inside that machine. And that signal ranges from low to high. So this is just a dimension ranging from low to high. And the average signal generated by a bag with a bomb is represented by this mean value here. It's pretty high up on the scale. So this is a decent machine. When there's a bomb inside that bag, it generates a fairly strong signal on average. But an important thing to realize is that not every bag with a bomb generates that exact signal. Some generate a slightly higher signal, some a slightly lower signal. So what you really have for the bags with a bomb, the targets, is a distribution of values. That's what that distribution is. That's its mean, and there's variability about that mean. And the same is true of the lures, the bags without a bomb. They don't generate no signal. I mean, they have stuff inside of them, maybe some high-density material in some of those bags, even though they're not bombed. So they generate some signal on average. But since this is a halfway decent device, the signal that the lures generate on average is somewhat lower than the signal that the bags with a bomb generate. So that's good. It really does separate, on average, bags with a bomb versus bags that don't have a bomb. But again, there's variability about that mean for the lures as well. And the whole problem, what makes this a difficult problem for a device, is that these distributions overlap. And so there's no signal strength that completely separates bags with a bomb from bags without a bomb. They overlap to some degree. And so you have to pick a value above which to sound the alarm. And that value I have just illustrated here. That's the criterion. And so anytime the machine is set, the knob is set such that anytime the signal is greater than that value, the alarm goes off, the bomb alarm. There's a bomb in that bag. And if it falls below that signal strength, it doesn't sound the alarm because it's decided that there's no bomb. And you can see that some of the lures are going to sound the alarm. In fact, as I have it drawn here, these are the lures, and 16% in red here exceed that criterion and sound the alarm, which is a bad thing. But most of the targets sound the alarm too, which is the way that it should be. And I don't know if you can see it, but about 84%, this now shaded in blue, 84% of that target, well, that's purple on that screen, 84% of the target distribution exceeds that criterion. So the hit rate is 84%. So when I said earlier that the hit rate is 84% and the false alarm rate is 16%, that's how you conceptualize it in the standard signal detection picture. You draw the distributions, you set a criterion on there. All right, and then I said you adjust, the false alarm rate is too high, so you want to adjust that sensitivity. You want to make it less responsive to that internal signal. And so you turn the knob and you set a higher criterion. It's not going to respond to the signal like it used to. And by doing that, notice that many fewer lures sound the alarm. Only 2% now sound the alarm of a bomb, that there's a bomb in the bag. And the price you pay, of course, is that the hit rate goes down to 50%. So now we have a hit rate of 50% and a false alarm rate of 2%. We adjusted the amount of signal needed to sound the alarm. Notice that we're not affecting the distance between those two distributions. To do that, you'd need engineers to build a different device. They've built this device, and it has a certain ability to separate targets from lures. We're just investigating the behavioral characteristics of this device, and we're seeing how it responds when we turn that knob, and seeing how the false alarm rates, hit rates and false alarm rates change together. And that is ROC analysis. So now let me move on to a second example that is one of the most clever examples. So Lorraine Allen and Shepard Siegel have a paper published in 2002. It's a signal detection analysis of the placebo effect. They actually review that literature. They don't report new data. And this is another place where it's helpful to think in terms of signal detection theory. So the procedure, and I'm simplifying a bit, imagine that you hook up a subject to a device, hook up electrodes and things, and the experimenter throws a switch. And sometimes when he throws that switch, it really delivers a mild shock, and sometimes it doesn't. So again, we have two states. You're either delivering a mild shock or you're not. And you deliver the pain stimulus or not, and you ask the patient or the subject, did you feel that painful stimulus or not? So that, remember, as soon as you hear a question like that, you should know this is a place where signal detection theory might apply. And then you study two conditions, placebo or no placebo, because you want to know, when you give somebody a placebo, does it reduce their pain experience? Okay, because that's the question. Now, let's think about this in signal detection terms. And step one is to draw the picture. That's always step one. It's something, if you really want to know detection theory, you should practice doing this. It's rewarding, actually. So there's some internal pain sensation, theoretically. So it's like a bomb detection device, except for now it's inside of a human being. There's some pain sensation that ranges from low to high. And on target trials, when you flip the switch, you really are delivering a mild shock. And because you are, the average pain sensation is relatively high up on this pain sensation scale. But again, there's variability from trial to trial. It's not the case that every time you deliver an electrical stimulus, even if you keep the current the same on every trial, the subjective experience of it is going to vary from trial to trial. Sometimes the individual might have their attention completely focused on something else, and so they'll hardly even feel the pain. Other times they might be concentrating intensely on the fact that a little shock is coming and it might hurt even more than usual. But on average, it hurts that much, and there's variability about that mean. Now, here's the surprising thing. What people doing this kind of research never stop to consider is that When you flip the switch and don't deliver an electric shock, the person will also sometimes experience pain. They don't think about that, but it does happen. On average, it's going to be a low pain sensation when you look within and try to decide, are you feeling pain? You're not going to feel much pain on trials where no electrical stimulus is being delivered, but there will be variability about that mean, and sometimes you'll actually feel pain when nothing happened. That's the distribution. And you'll actually report that you felt pain on that trial. But this is not something that these placebo researchers ever gave any thought to, and so they didn't even include those trials. But if it's like this, and you do include those trials, you might find that about 16% of the time, the individual says, yeah, I felt some pain on that trial, even though no shock was actually delivered. There is a false alarm rate. And 84% of the time they'll feel the electric shock when it's delivered. And 16% of the time they won't even feel it, possibly because their attention was diverted elsewhere or for whatever reason. But their criterion is set somewhere on that pain sensation scale. And anything above that criterion, they announce that they experience some pain. And so now you want to know, what does a placebo do? And you give somebody a placebo, and you might find that, as they do find, it reduces the hit rate down to 50%. That is, it used to be the case that when I delivered the electrical stimulus, 84% of the time they said they felt it. I give them a placebo, and now they claim to feel it only 50% of the time. And the conclusion is, therefore, a placebo decreases the pain sensation. That is, what they're thinking is that it decreases the distance between these two distributions. They're actually feeling less pain when they're on the placebo. But a signal detection analysis raises the possibility that that's not what's happened. You haven't changed the degree to which the electric shock causes them pain. All you've really done is induce them to set a higher criterion for reporting pain. And the way you know that is if you looked at what happens on those trials in which no painful stimulus is delivered. And in these studies, what you do see is that the false alarm rate goes way down as well, such that what has happened is they've set a higher criterion. You've given them a placebo, and they know that they've taken a pill, and it's supposed to cause less pain. And their sensitivity, their reaction to pain is the same. They still feel it as much as ever. The distance between these two distributions is the same as it always was. They're just less inclined to report the experience of pain. Okay? And Allan and Siegel review literature suggesting that this is always what you get, almost always, in placebo studies. If you look at both the hit and false alarm rate, you see that it's a criterion shift. They don't actually feel less pain. Whereas if you gave morphine or something like that, it really would decrease the hit rate, even if it didn't affect the false alarm rate. You'd bring those two distributions closer together because you'd be feeling less pain. Okay, here's another example, a list of words in a laboratory. A cognitive psychologist will use a procedure like this. Give somebody a list of words, and then follow it by a recognition test in which you randomly intermix targets and lures. So the targets are the words that appear on the list, and the lures are the words that didn't appear on the list. And you just ask them for each word, randomly intermix and present it one at a time. Was this word on the list, yes or no? And if they think it was on the list, usually they call them old new judgments in this literature. So if it was on the list, the subject is supposed to say, this is an old word, it was on the list. If they think it wasn't, like drama, they say, oh, this is a new word, it was not on the list. And you might see that a check mark means they declared it to be old. You might see about 8 out of 10 of the targets are correctly declared to be old, and about 2 out of 10 of the lures are incorrectly declared to be old. So again, a hit rate of 0.80, false alarm rate of 0.20. Again, the same picture applies even in this situation because it's that kind of decision. And I have it drawn such that the hit rate is 0.84 and the false alarm rate is 0.16, similar to the example I just showed you. And now it's memory strength that's varying. The targets have a relatively high memory strength on average. The lures, they don't have no memory strength, even though they weren't on the list. You know, when you're trying to decide, did I see this before? Even those lures generate some sense of prior occurrence. Okay? So, behavior analysts probably don't like that too much, you know, a trace strength, something like that. And here's a big secret about classical detection theory that I want to let you all in on in case you don't know it. You don't have to call that memory strength if you don't want to. In fact, you can call it something else like internal state. And in fact, you don't have to call it anything. You don't have to name that axis in classical detection theory. And here, I'll prove it. It's gone. And nothing has changed. We still have a hit rate of 0.84 and a false alarm rate of 0.16. We still have our two distributions. We still have a criterion. That's a 16% area there. That's an 84% area there. You don't have to name that. You're not required to name that. In fact, we don't really know what it is. We can't see inside the organism's head. We call it, the reason I call it memory strength and pain sensation is because it makes it concrete and simpler to understand. But my advisor in grad school, Jack McDowell, used to always quote this back to me. Philosophy is a battle against the bewitchment of our intelligence by means of language, by Wittgenstein. Same is true of psychology. You know, it's just a tool. It's not. You shouldn't conclude that we really think we know what that unidimensional scale is. We don't know. We can't see it. We can't measure it, and we don't have to know. It's just that it's helpful to label it memory strength and make it concrete. And sometimes they even put numbers on the scale, even though we obviously don't know if it's what memory strength is, and we obviously can't measure strength of a memory trace. But it's helpful to make it concrete just to make it understandable. Okay, so let's get. I'm going to stick with memory strength for a while. And this is that same situation, but now I'm going to do to the human subject. I'm going to adjust their sensitivity knob to make them either more or less likely to declare that the item was on the list, but without changing their memory. So you don't do anything to change their memory. So you present a list of words at a certain rate and then test their memory for it. And the previous example, the hit rate was 0.84 and the false alarm rate was 0.16. And now you do it again, a different list of words. You hold the memory characteristics the same. Let them study this new list for the same length of time as they studied the old list. So they memorize it to about the same degree. But you say to them, this time, I don't want you to declare an item as being old, as having appeared on the list, unless you are quite sure that it appeared on the list. Only if you are quite sure should you say that it appeared on the list. And what they will do is, conceptually, set a higher criterion. They'll move it from the middle, and they'll set it higher. And again, both the hit rate and the false alarm rate will go down because of that. And then another group of subjects, or a different condition with the same subjects, you give them a list to memorize and tell them, feel free to guess. If you have the slightest sense that this word appeared on the list, say that it did. Guess wildly, and they'll set their criterion far over to the left, which will increase both the hit rate and the false alarm rate. Okay? We can do that. And in fact, looking at this picture, let's go back to the conservative condition. If they kept adjusting it farther and farther, becoming more and more conservative, the hit rate and false alarm rate would keep going down until when it was out here, both the hit rate and false alarm rate would be 0. That's how conservative you can become. And similarly, if this criterion kept going to the left, when it's out here, you'd call everything old. Everything would fall above that criterion. All the lures and all the targets. So you'd have a hit rate and false alarm rate of 1.0. So one end of the scale is 0, 0, the other end of the scale is 1, 1, and everything in between are hit and false alarm rates like that. And so you have lots of pairs of hit and false alarm rates. And what are you going to do with those pairs of hit and false alarm rates? Well, what you can do, it's really simple, is just plot hit rate versus false alarm rate. Simple as that. Just plot them, hit rate versus false alarm rate. And when you do, you get a plot like that. That's the hit rate. It would go all the way down to 0, 0. It would go all the way up to 1, 1. And these are just the hit rate. And this point is the 0.84, 0.16 that I've been talking about the entire talk. And that is an ROC. That's a receiver operating characteristic. And they often look just like that, whether you're talking about pain sensation, a bomb detection device, a human in a memory experiment, a clinician trying to diagnose autism. In all of these cases, when you do it, it turns out looking like that. Isn't that great? So why would you want to do that? It's not obvious why you'd want to do that necessarily. Well, earlier, just to back up for a second, when you're talking about a bomb detection device, you'd want to know its characteristics. And so you could think about what is the optimal setting. And first you'd do a behavioral experiment with this bomb detection device and trace out the ROC. You change its sensitivity knob, run a bunch of targets and lures, get a hit and false alarm rate, change the sensitivity again, get another set of hit and false alarm rates, and you'd trace out the whole ROC so you could think, now you've got the ROC and you can sit around and decide, well, should we set it there, or should we set it here where the false alarm rate is almost 0, and we still have a hit rate of about 33%, so at least we have a chance of detecting a bomb and we'll hardly ever have a false alarm. Maybe that's where we want to set it. So there are practical reasons for doing it, but there are other reasons. So as signal detection theory, as I just sort of intuitively tried to communicate, predicts a curvilinear ROC like the one you just saw. Other simple and intuitively appealing theories predict a linear ROC. That is, other simple models predict a linear ROC. High threshold theory is one. You may not have heard of that. It's been gone for a long time. But it's repeatedly reinvented and rejected because its inconsistency with detection theory is not readily apparent. And here's the key. It's easy to come up with models that make a lot of sense and that are intuitively appealing. but it doesn't jump out at you that these models predict a linear ROC. And so it's not jumping out at you also that this theory contradicts signal detection theory. And you may want to contradict signal detection theory, but it's something you should do with your eyes open, not your eyes closed. And usually people do it with their eyes closed. They propose a theory that makes a lot of sense, not realizing that they are rejecting signal detection theory, which they may not really want to be doing. So I'm going to give you an example of that from my laboratory from a while ago. So now I'm switching to pigeons. We talked about bomb detection, pain sensation, humans with a list of words, and now these are pigeons in a Skinner box. And this is time going down. And this is just, I started investigating this procedure a long time ago because it was like, it struck me as the perfect signal detection task for pigeons. So on some trials, they're sitting in a dark ITI. This is the ITI in dashed lines. And then a trial starts. And some trials are just nothing trials. So it's the start of a trial according to the experimenter's computer, but from the pigeon's point of view, nothing actually happens. It's a nothing trial. So they're still sitting in darkness during this, say, 4-second retention interval. The bird is sitting in darkness this whole time. As far as it knows, nothing has happened. And then the red and green choice keys pop on. And what the bird has learned over many trials is to peck the red key if nothing happened. That means, that's the bird's way of saying, I think there was no sample on this trial. And it gets some food. That's what that plus sign means. And then there's a dark ITI. And on another trial, something might happen. This is a sample trial. We actually present a 10-second house light, let's say. So something actually did happen. And then it goes back to darkness for a 4-second retention interval. And this time, can't see, it's kind of off the bottom of the screen. They have to pick the green key. That's where the reinforcer is available. So the birds learn to do this task just fine. And remember, it's a detection task. Did the sample occur or not? That's what you're asking the bird to report, and they can do it just fine. And when you run a study like this, you can vary this retention interval. That's a nominal retention interval on these trials, and it's a real retention interval on these trials. And just see what happens. And you usually see data like this. Let's look at the no-sample trials. These are the trials where nothing happens, and they're about 80% correct, a little better than 80% correct, and it doesn't matter what the retention interval is. You increase the retention interval, they stay about 80% accurate, and we've done much longer retention intervals, and they keep staying accurate. 80% correct, and it doesn't change. Whereas on sample trials, they start off accurately, so after 1 second, they remember the sample, so they peck the green key, and they get their food. But as that retention interval increases, they forget that a sample occurred. And when they do, performance drops off dramatically. And finally, this is 50% correct. They fall well below 50% correct. Okay, so that's the pattern of data. You see it all the time with this task. And the question is, how do you explain this? What's a simple theory that would explain this? So I'm going to tell you a simple theory that nicely accounts for this. It's called, one way of referring to it as a default response model. And so here's the story. The bird just has some kind of default response, default bias to choose the red no sample key. It just has that bias, and it's going to do that if nothing gets in its way. So with probability P, choose, more formally here, with probability P, choose the red alternative. And that probability was about 0.8 in the data that I just showed you. So that's the bird's default bias, and it's just going to do that if nothing gets in its way. Okay? And Q is 1 minus P. I'll talk about Q. That will become the false alarm rate. But right now, its default strategy is to choose the red key with 80% probability. And on no sample trials, it always uses that default strategy. There's nothing to get in its way. Nothing happens on a no sample trial. It doesn't matter how long the retention interval is, nothing happens. And nothing gets in the way of that bird's inclination to choose the red key 80% of the time. So it just relies on that strategy no matter how long the retention interval is. You can make it 90 seconds long, and it's still with 0.8 probability going to choose the red key and usually get the answer correct. But on sample trials, something does get in the way of that default response. So if the memory trace is present, which happens with probability M, let's say, then the bird should choose the sample alternative, the green key, because that's where the reinforcer is, and the bird learns that if a memory trace is present, that's where the reinforcer is. But if the memory trace is absent, which happens with probability 1 minus M, they revert to that default strategy of choosing the red alternative 80% of the time. And as the retention interval increases, the probability that the memory trace is absent increases. So after a long retention interval, it's just like a no sample trial. The memory trace is gone, and there's nothing to get in the way of their default strategy, and so they are choosing the red alternative again. So I don't know if that's intuitively appealing to you. This model made sense to me when I first heard it. Now, I'm going to tell you about a signal detection analysis of these data and how it differs from that simple model in just a second. But here's some terminology. Choosing sample on sample trials is a hit. That's a percent correct measure. choosing sample on no sample trials is a false alarm. That's what Q is. In detection terms, the false alarm rate remained constant at 20% on those no sample trials, and the hit rate dropped from about 90% down towards 20. So if you plotted those exact same data as hit and false alarm rates, so now we're doing the proportion of sample choices. Here's the hit rate. That was on the earlier graph, and now this is 1 minus what was on the earlier graph. This is the false alarm rate. So the false alarm rate is remaining constant. And again, here's the default response model. Sometimes it's simpler to think about it as a diagram. And here's what happens on sample trials. If the memory trace is present, which happens with probability M, you choose the green key because that's a hit. And that's a hit. That's where the food is. With probability 1 minus M, the trace is gone. But you engage in your default strategy, and sometimes the default strategy is to choose green. That with 0.20 probability, you choose green. That's another way to get a hit. There's 2 ways to get a hit on sample trials. Either you remember the trace or you don't remember the trace, and sometimes when you engage in the default strategy, you choose green. So 2 ways to get a hit. Usually, though, your default strategy with 80% probability is to choose red, and if the sample really was presented, that's called a miss. On no sample trials, nothing gets in the way of the bird executing their default strategy. With probability Q, choose green, so there's a 20% false alarm rate. 80% of the time, choose red, and they do that no matter how long the retention interval is. So that's the default response model. Simple way of thinking. It fits with these data. It explains why performance on the sample trials goes to below 50%. It's because eventually the memory trace is gone, and they're just doing this default strategy, which is to choose the wrong answer 80% of the time. Okay, so from that way of thinking, you can derive these basic equations. And this is usually, one wouldn't do this unless one's wondering if this differs from the predictions of signal detection theory. So I just said the hit rate is equal to the probability that the memory trace is there, M, plus 1 minus M times the probability that you choose the correct key anyway due to the default strategy. So that's what the hit rate equals. The false alarm rate equals Q, just the probability of that 20% chance of choosing the green key by default. And, well, a little algebra, that's Q and that's Q. You can plug false alarm rate in for that, and it becomes this equation. The hit rate equals M plus 1 minus M times FA, which is in the form of a straight line. So this theory, this simple theory, which makes sense of the data, says that if you hold memory constant, let's say the 4-second retention interval, we're not varying that, so the distributions, the distance between them is not changing, and you just bias them in various directions, so you change the hit and false alarm rates together, like adjusting that sensitivity knob, the relationship between hit and false alarm rates should be a straight line. That's what this simple model predicts. And it doesn't jump out at you when you're thinking about that simple model that that's what it predicts, but if you work it out, it is what it predicts. And so you can do the experiment. You can bias birds around too. It's a little more trouble, but the way you do that is this is how you'd bias them towards a no sample alternative. On no sample trials, they get a reinforcer with probability 1.0 as before, but on sample trials, you can't see it there, but a probability for a correct choice of a sample alternative is reinforced with, say, probability 0.2. So they're still getting reinforced for a correct choice, but at a much lower probability. And this is going to make the bird like the red key much more than the green key. And they'll choose red more often. And in detection terms, what you've done is what's shown in this upper panel. You've biased them, so their choice is to choose the sample key or the no sample key, and you've just biased them in the conservative direction. It's the no sample key that has most of the goodies, so they're going to move the criterion up, which is going to decrease the hit rate and false alarm rate. And then in another condition, you can switch the reinforcer probabilities and bias them the other direction, and you're going to raise the hit and false alarm rate. And you can just do this biasing manipulation, and then you'll have several sets of hits and false alarms, and you can plot them against each other to see what the path is that they trace out when you hold memory constant at a particular retention interval. It should, according to detection theory, trace out a curvilinear path. And what you see in data are things like this. So here's the 4-second retention interval. They trace out a curvilinear path at that memory. Here's a different memory strength. Again, they trace out a curvilinear path. Here's a different memory strength yet. I don't show the straight line fits, but the straight line fits are much worse than the curvilinear fits. In every case, you get a curvilinear ROC. And so the relationship between hit and false alarm rate is curvilinear. Almost always is. That's why you should be nervous if you come up with an intuitively plausible account that predicts a linear ROC. You should worry about that because there's a good chance when you do the experiment you're going to find out that it's a curvilinear ROC. And the default response model, which used to be called the high threshold model, is wrong. High threshold model in recognition memory was rejected long ago precisely because it predicted the wrong shape for the ROC, not for any other reason than that. And people don't believe it anymore, but it gets reinvented. And when it's reinvented, people don't say, oh, this is high threshold theory again. They give it a new name, like the default response model or something like this. And it's been reinvented in several domains, always with a new name. And you always have to stop and think about it and ask yourself, what does this predict about the relationship between hit and false alarm rates? And you often find out it predicts a linear form. And the data are, the fact that you get a curvilinear ROC doesn't prove that detection theory is right, but the data are compatible with a signal detection account, which is usually the case. Now, here's something else you can do with an ROC. So there's a hypothetical ROC again. Data off from very many experiments trace out a path like this. And there's more information that you can get out of this that's interesting and worth knowing. So what's not obvious, but what's the case, is that if those distributions that I've been drawing if the underlying distributions are Gaussian in form, if they're bell-shaped curves like that, then you should get this curvilinear ROC. But it makes a more specific prediction than that. If you transform these hit and false alarm rates to z-scores. So hit rate of 0.84, look it up in a z-table, that's a z of 1. False alarm rate of 0.16, look it up in a z-table, that's a z-score of -1. If you just transform those hit and false alarm rate probabilities into z-scores, take that step. So now you have pairs of z-scores instead of pairs of hit and false alarm rates. Now it should be the case that they trace out a linear path. This is the case in which they should trace out a linear path. And when you do that, it's almost always the case that the ROC is linear. Like that. This thing keeps switching on me. It's a straight line. And so this is how people usually do ROC analysis. They transform the hit rates and false alarm rates into z-scores. It turns out that it has to be a straight line if those are Gaussian distributions, but other distributions can also produce a straight line. So this doesn't prove that it's Gaussian. However, there are lots of distributions that won't produce a straight line in z coordinates. So it's an opportunity for detection theory to fail, or at least the Gaussian version of detection theory, and it usually passes this test. The other interesting thing is that theoretically, I won't go through the math, but if you did go through the math, you'd find out that the slope of this line gives you a really interesting piece of information. It is theoretically equal to the standard deviation of the lure divided by the standard deviation of the target. So in all the pictures I've shown you thus far, the two distributions have equal standard deviations. It's an equal variance model, it's called. But that's really unlikely to be observed in practice. I mean, that would be a miracle if your experimental manipulation had no effect on the variability of the distributions. And the slope of this line tells you, theoretically, what the ratio of standard deviations is. And often in human memory experiments, for example, that ratio comes out to be about 0.8, which means that this is the signal detection picture that applies. These are Gaussian distributions, so an ordinary ROC is curvilinear, a z-transformed ROC is a straight line, and the slope of that line is 0.8, which means that the standard deviation of this distribution is 0.8 times the standard deviation of that distribution, and that's the standard signal detection model of human recognition memory, unequal variance model. Okay, so that's other information that you can get out of ROC analysis. All right, well, there's a little bit more that's really interesting about ROC analysis. And if you're running human subjects, it's really easy to get ROC data. It's trivially easy. And all you have to do is ask, instead of just asking for an old new judgment, which is what people usually do in a recognition experiment, also ask them for their confidence in that response. So their confidence that it's an old item. It takes almost no more time. Subjects don't mind giving you that information. And what you find if you get that information is something really useful. In fact, you can construct an ROC from just one trial. You don't have to have different biasing conditions. You can do it that way, bias them in the conservative direction, bias them in the liberal direction, but you don't need to. You can just get confidence ratings, and you'll have in your hands the information you need to construct an ROC. So I'm going to show you how to do that in case you ever want to do it. And it's any kind of task where you're asking for a presence versus absence or response. You can also ask for confidence. And you should, because it gives you a lot more interesting information. So let's just think about how that's done. So here are the two distributions again. Here's my decision criterion right in the middle again that I've been talking about the entire time. And it'll generate a hit rate of 84% and a false alarm rate of 16%. But when you ask for confidence, what that theoretically is, according to the standard detection account, is it's a response in relation to additional criteria. There's not just one decision criteria, there are several. So for example, if you have something that generates a memory strength way out here on the axis, way up here, let's say, that's a very strong memory. And you might not, it exceeds your old-new criterion, so you'll say old, but you'll also say it exceeds this even higher criterion, the old sub-high criterion, and you'll give it a high confident old response. Not only am I saying that it's old, I'm saying it with high confidence. I'm positive this is an old item. And anything that falls in this region above this criterion, the old sub-medium criterion, but below the old sub-high criterion, you say old, but with medium confidence. And anything that falls in this range, you say old because it's above your old new criterion, but you give it low confidence. It's above your old sub-low criterion. And same with new. Anything in here, you say new with low confidence. Here, new with medium confidence. Anything that's a low memory strength, like way out here, is so low in memory strength. You not only say this is a new item, you say I am positive this is a new item. This did not appear on the list. Okay? So what you have in your behavior, that's the conceptualization. What you have in your hands are the behavioral data, the confidence ratings. And you can use those confidence ratings like this to construct an ROC to see what it looks like. So what you do basically is you take one criterion at a time and you just pretend that that is the old new criterion. Really, this is the old new criterion. Anything above this got an old response. Anything below this got a new response. But for purposes of constructing an ROC, you're just going to pretend for a moment that this is the old new criterion, this high confident criterion. So you're going to pretend that anything that got a high confident response is an old judgment, and anything that got anything else is a new response. So the hit rate, the false alarm rate is very small. Only a small percentage of the lures fall in that region. That's the false alarm rate of about, so this is the proportion of items that exceed the O sub H criterion. It's a very small number. And you're calling that the false alarm rate. And then you can look at, for the hit rate, you can just calculate the proportion of targets that got a high confident old response. And in this example, it's about 31%. So that's a hit rate and a false alarm rate. Now really they said old to some other items, but you're pretending all those other responses are new judgments just for the moment. Okay, so that's one pair of hit and false alarm rates. And now you can compute a second pair. So here's a false alarm rate using the medium criterion. Anything that got an old, medium, or higher judgment, that is anything that got a medium or high confident old response, you're for the moment pretending that those are the only old responses and treating everything else as if it were a new response. And so now the false alarm rate is the proportion of lures that got either a medium or high confident old responses. So now that's about, you're summing across, you're accumulating across those, and the false alarm rate is about 6%. And the hit rate now is all the targets that fell above the medium criterion, and that's about 66%. That's all those items in there. And you just keep doing that, accumulating everything that got a response that high or higher, and calling that and computing your hit and false alarm rates accordingly. And so now you'll have 5 pairs of hit and false alarm rates just from your confidence ratings that your subject gave you. You didn't have to bias anybody to the left or to the right. You just got confidence ratings, and you computed hit and false alarm rates that way. Might seem tricky, but it's not that bad. Now we can plot these hit and false alarm rates against each other, which people do. They do this all the time, and it always comes out looking like that. And human recognition memory experiments anyway. Turn them to, oh wait, hold it, that's in the wrong place. Turn them to Z-transform coordinates. They trace out a straight line. This is confidence-based ROCs. And it's just a nice way to get some additional information. So let me finish off by talking about one more thing about these. So these regions of confidence, I was just talking about accumulating hit and false alarm rates in order to construct an ROC, which is a good thing to do. You want to know if it's curvilinear. You want to know what the slope of the Z-transformed ROC is, so you know something about the relative variances of the distributions. But sometimes it's worth not accumulating and just looking at the hit and false alarm rates non-cumulatively. So for the high confident responses, that's all these responses out here. And that was a hit rate of 31% and a false alarm rate of about 1% or less. And what's true, if you just look at those, almost all of those high confident responses were correct. Then you see this in real data. This is hypothetical data here, but you see this in real data. They're almost all correct when they give high confidence. Usually it's about 93% correct, but they're very likely to be correct when they say high confidence. And that's how it should be, because if you draw these distributions and draw a high criterion, you'll see that there's a lot of targets still above that high criterion. There's very few lures. So the odds are they're going to be correct when they give a high confident response if a signal detection model applies. But in this medium range here, there's still a lot of targets, but there's more lures. I mean, there are more lures than in the high confident case. So it's still going to be doing pretty well, but you can see the hit rate in this region in between criteria is 34.8%, and the false alarm rate of about 5%. So overall percent correct is about 88% correct for the medium confident responses. And for the low confident responses down here, that's in this region right here, you can see there are a lot of lures. See how the height of that lure distribution in this region in here is pretty high. So the hit rate is 18.5% of the targets fall in that range, and about 10% of the lures. So percent correct is about 64% correct. So it's it might seem perfectly natural that when subjects are highly confident, they're accurate, and when they're not so confident, they're less accurate. But actually, that's pretty miraculous. Somehow, they have learned to be that way. They have learned to pay attention to this internal state and to respond accordingly. And that one, that's the one. That one that was out of place. When you do change D prime, when you make the memory conditions less favorable, what you find is that they adjust the criteria to maintain that high accuracy confidence relationship. So they know to move the high criteria, if it's a poorer memory condition, so the distributions are closer together, they push out that high confident criterion, so their high confident false alarm rate, which is low to start with, actually gets lower. Because I won't go through it, but you have to do that to maintain a high probability of being correct. And people actually do this in memory experiments. And cognitive theorists, it's an amazing thing. To explain data like this, which I realize I'm only giving you the barest impression of, but to explain data like this, if you take a pure cognitive approach, you have to assume that people have these distributions in their heads, and they can compute likelihood ratios on the fly and to maintain this confidence-accuracy relationship. And it's pretty miraculous, and lots of cognitive theories do make that assumption. But this is why I think more behavior analysts need to study signal detection theory and investigate how others are using it in other areas, because really what this is almost certainly is just a reflection of the subject's learning history. They've learned to pay attention to their internal state, and they know when to express high confidence and when not to. And that's the way it is. You start off in life expressing high confidence in everything, and then the verbal community and experience teaches you, there are times when you shouldn't express high confidence. And you learn to pay attention to, I assume, the internal state that allows you to make those judgments, and over time you're trained up on that. And so you're not calculating ratios of Gaussian distributions in your head. When you see subjects doing that, you're seeing a reflection of their long learning history. But if you're a cognitive psychologist, you don't think about that. They walk into the laboratory, they behave in these miraculous ways, like they know signal detection theory, and it seems quite miraculous. So my conclusions, anyway. Signal detection theory makes the world a smaller place. That is, it's a language that a lot of people speak. And it's worth knowing for that reason alone. It's a way to communicate with the rest of the world. It's a non-intuitive model. I wouldn't say it's counterintuitive, but it's non-intuitive. And it usually illuminates rather than obfuscates. No matter where, usually wherever it's applied, it sheds light on the problem. ROC analysis is easy and informative, and if you can take confidence rating, it's even kind of fun. And behavior, even though it's classical detection theory, behavior analysts can use it to study how behavior maps onto internal states, because that's something that, I don't know, I remember studying behavior analysis in my early days and saying that behavior analysts don't really disagree that there are internal states. They just don't study them. And this is actually a way to study them without having to name them. You don't have to say that this internal state is made up of features that at the semantic level and connected interactively with the lexical level and all that. You don't have to make a Baroque theory of cognition to study that. You can study it usefully using detection theory, because it doesn't take you down that garden path to complicated cognitive theories. So, okay, that's my story. Thanks.
Very nice. Thank you very much. We have time for questions.
How do you get a confidence rating in an animal?
I don't know. In animals, that's why when I do it in animals, I bias them to one key or the other. I mean, if there's a way, some people have actually studied that, but yeah, you may.
Suppose you have reinforcement or the correct detection on every fifth trial. Responding will move more and more towards the detection as trials pass since previous reinforcement. Now, you have to assume that not responding is the equivalent of saying no. Brief trial, package yes, no package no. Other trial, package yes, no package no. On the fifth such trial, reinforcement is available for a correct detection.
Sounds like that would be a faster way of doing it. But you might also be able to look at reaction times, because some people, in a classical detection model, the farther from the criterion you are, the faster the response should be.
Not allowed to hit that reaction time and rates.
Who did that?
Not allowed.
Oh, not allowed to done that.
I seem to recall someone using a method where, for example, they had a fixed interval, and they said, well, the animals are more confident if they peck more times during the interval than if they did not. So if they peck only once, they're less confident than if they peck 5 times. And so they translated that into confidence.
Yeah, maybe that would work. I don't know. You'd have to add that assumption. Alan, you...
Well, it reminds me of some of the metacognition work, Sarah Shuttleworth and others, who are asking the pigeon to make a judgment of how sure are they of their decision, and the payoff matrix depends upon that. So you could actually, I would guess, get the pigeon to report its confidence.
True. Shuttleworth has tried to do that experimentally. I'd forgotten about that. I'm not sure if everyone would find it convincing, but it's a nice try.
You presented an Allan Siegel article about the placebo effect being adjustment upward. Can you work with confidence intervals of the placebo effect?
Have they looked at confidence intervals of the placebo? Do you mean, have they looked like statistical confidence intervals or confidence ratings from subjects? Oh, how confident are you that you feel pain? I don't know if anybody's done that. That would be kind of a interesting way to look at it. I don't know. Not in the they reviewed the literature, and so few people have taken a detection approach. I doubt anyone has given that a try to see what you'd get.
Most of your applied examples involve discrete stimulus presentations. Yet in the applied world, there are some kind of continuous stimulus presentations, such as pain stimulus which modulates up and down and stuff like that, such as a headache on company. Is signal detection theory equally applicable to kind of continuous presentations where the issue is when does it become painful and modulation is thereon?
Yeah, it is. It's naturally extended to those situations. Psychophysicists study situations like that all the time, continuous variable. And what you have is a continuously moving distribution up a scale. And some standard psychophysical methods are just straightforward extensions of detection theory to problems like that. It's more complicated, but it isn't immensely complicated. And it's still the case that it's illuminating when you think of it in those terms. But
I sometimes have a lot of trouble figuring out whether an operation will move the bias or whether because I mean it isn't obvious when we try to fix the machine from the outside to say do something that would improve T5 as opposed to doing something that would change bias. What about operations that operate systematically on one part of the equation rather than the other? For example, that put in punishment for not responding to exposure, or for one kind of response to exposure to another. I mean, is it then possible to operate distinctly on on hits versus false alarms?
Yes, so for example, a way to manipulate hits without affecting false alarms, for example, would be, so I told you that about that presence versus absence procedure with pigeons. And ordinarily, and evidence is consistent with this, neither animals nor humans shift their criterion around much trial by trial. Typically it's set within a session. Both humans and animals. You can make them switch it, but if you don't, one can argue that they leave it set. Which is why, in those data I showed you, I have to go through all those things. The data from this experiment, that's evidence right there that the hit rate's going down, but the false alarms remaining constant because they're not moving that criterion against that noise distribution. That noise distribution isn't changing. That criterion isn't changing as a function of retention interval. But the signal distribution is weakening with retention interval, so you're selectively affecting the hit rate. So, I mean, it can be done, but that's the easiest way. Within a session, manipulate, say, the strength of a memory trace or something like that.
Thank you all for a lot of good questions.
Thank you.